Imagine this for a second. It's a scenario that really tests pilot skill. You're airborne, just climbing out from the runway in a big Boeing 777. Everything feels totally routine, a standard takeoff. The autopilot's auto throttle system is engaged, set nice and efficiently to CLB2. Seems perfectly normal. But then suddenly, as you're climbing, you see it terrain. It's much closer, maybe higher than the turret suggested, than you anticipated. Now, crucially, there's no engine failure. Nothing's broken. The plane's fine. But you absolutely need more thrust right now to increase your rate of climb and make sure you clear that obstacle. So what are the exact steps a pilot takes in that critical moment? Welcome to the deep dive. This is where we take your detailed questions, dig into the sources you send us, and try to turn it all into, well, crystal clear insights. Today, we're diving right into the heart of flight operations, exploring that precise situation. How do pilots get that urgent boost in climb performance when something unexpected happens, even when the aircraft itself is working perfectly?
Yeah, it's a really fascinating question. It gets right to that balance pilots constantly manage between running things efficiently day to day and the immediate overriding need for safety. We'll be looking at the very specific actions pilots are trained for, pulling details straight from the official Boeing 777 flight manuals. It's quite revealing about how deep the safety procedures go.
Okay, let's break this down then. The scenario says you're already airborne, so you're past V1, that's the point of no return on the runway, right? You're committed to flying. And you're in a normal takeoff phase, auto throttle set to CLB2. So first things first, what does CLB2 actually tell us about the engine thrust? Why use it? It sounds like you're deliberately not using full power.
That's exactly right. CLB2, or Climb 2, is what's called a derated thrust setting. It means you're using less than the maximum available thrust from the engines for the climb phase. It's very common practice during normal takeoffs and climbs. Pilots often use reduced thrust, like a fixed derate, which is pre-selected. Think of it like setting your car's cruise control slightly below the maximum speed it could go. You do it for efficiency, engine health.
Okay. So it's a planned reduction, not just a default.
Absolutely planned. The sources show pilots select these settings like full rated thrust or a specific percentage derate, maybe even something called takeoff bump for specific conditions, right there on the CDU on the thrust limit page before takeoff.
And the benefits are?
Well, primarily, it significantly extends the life of the engines. Less stress means less wear and tear. It also saves fuel, which is always a major factor, and can even reduce noise impact around the airport. It's all about optimizing for the long haul and the specific flight conditions.
Got it. So efficiency is key in normal operations. You're cruising along, conserving fuel, being kind to the engines, holding some power back in reserve. But then, boom, unexpected terrain. Suddenly, efficiency isn't the priority anymore. Safety is. You need that reserve power, and you need it now. How does the pilot actually get to it? My first thought would be just, push the throttle levers all the way forward. Is it basically that simple?
Well, the instinct is right, but there's a very specific procedure and condition attached. This is where the flight crew training manual gets really precise. It poses that exact question. When can you push past that preset, fixed derate limit? Because it's not just a free-for-all. There are rules.
Rules even for getting maximum power in an urgent situation. Okay.
Exactly. The manual is quite clear. It says the thrust lever should not be advanced beyond that fixed derate limit unless specific conditions occur during the takeoff phase where, and this is the key phrase, additional thrust is needed on both engines.
On both engines. That sounds important. What kind of specific conditions are they referring to? Does our scenario suddenly seeing terrain fit the bill?
Yes, it absolutely fits. The manual gives a couple of examples. One is encountering wind shear, a sudden nasty shift in wind. And the other, directly relevant here, is if after V1, increased accelerations is needed to complete the takeoff. That phrase, increased acceleration, directly covers needing a higher rate of climb. So seeing that terrain unexpectedly looming means the conditions are met. The procedure is then to manually advance the thrust levers.
Okay, so the manual specifically expects even the pilot to override the efficient setting for safety to get that climb performance. And that emphasis on both engines seems critical. Which brings us to that really important detail we set up at the start. Our scenario explicitly states, no engine failure has occurred. Why is that distinction so crucial? It feels a bit counterintuitive. Wouldn't you just want all available power from any working engine in an emergency?
This is where the depth of the training and aircraft handling really shows itself. It's a perfect example of why just saying more power isn't always the right answer in aviation. The manual has a stark warning about this. It states, and I'm paraphrasing slightly, If an engine failure occurs during takeoff, increasing thrust beyond the fixed derate limit on the remaining engine could result in loss of directional control.
Loss of directional control just from adding power to the good engine. That sounds bad.
Extremely bad. Think about it. You've already got asymmetric thrust because one engine isn't working. If you then firewall the other engine, you make that asymmetry much, much worse. It's like trying to paddle a canoe really hard but only on one side. The aircraft would yaw very strongly towards the failed engine. At low speed and low altitude, right after takeoff, trying to counteract that massive imbalance while also climbing could be incredibly difficult, maybe impossible. It risks losing control of the aircraft's direction.
Wow. Okay, that's a huge difference. So the same action pushing the thrust levers forward has completely opposite safety implications depending on whether one engine has failed or not. That pilot assessment before acting has to be almost instantaneous then. How do they make that call under pressure?
It's drilled into them through intense training, simulator work, you name it. An engine failure comes with very specific warnings, lights, sounds, instrument readings showing 0N1 or EGT dropping, and the aircraft physically pulling to one side. It's usually pretty unmistakable. If all those signs are absent, and the problem is simply needing more climb performance, then the procedure is clear. Advance both thrust levers. It's a rapid diagnostic process. Engine failure? No. Terrain issue? Yes. Action. Increase thrust on both.
That clarity under pressure is just
Yeah.
remarkable. Okay, so the pilot identifies the need, confirms both engines are good, and decides to push the levers forward. What's happening with the auto throttle system during this? Does the pilot have to disconnect it first, or does manually pushing the levers override it somehow?
Good question. The pilot can disconnect it, but they don't necessarily have to in this specific context. The system is designed for this kind of manual intervention. When the autopilot is in a mode like FLCH, SPD flight level change speed, where it's using pitch and thrust to maintain a selected airspeed during climb or descent, the autothrottle has a feature allowing it to go into hold mode.
Hold mode, what does that do?
It essentially means the autothrottle acknowledges the pilot is now manually controlling the thrust levers and stops trying to manage the speed itself via thrust. The flight mode enunciation will actually change to show hold. Once it's in hold, the autothrottle is passive regarding thrust commands. The manual explicitly says that in this mode, thrust levers can be manually advanced. So the pilot physically pushes the levers forward, the autothrottle registers this override, goes into hold, and lets the pilot command the required thrust directly.
So it's a built-in feature, essentially. The system recognizes the pilot taking charge of the throttles in that mode.
Exactly. It's a design pathway for manual control when needed. We also see manual thrust commands with the TOGA switches, takeoff, go around. Pushing those is another way pilots command maximum available thrust very quickly, often during a missed approach or indeed during the initial takeoff roll itself.
Okay, that makes sense. It's a deliberate physical override mechanism that's part of the system's logic, not fighting against it.
Precisely. The human pilot remains the ultimate authority, especially when immediate maximum performance is needed for safety.
Right. We've really gotten into the weeds of the procedure here, the how-to. But let's pull back a bit. What's the bigger picture here? What does this scenario and its specific solution tell us, maybe even surprise us, about how these complex systems work? What's the key takeaway for you, the listener, trying to understand these critical moments in flight?
I think the main takeaway is this. Modern aircraft are incredibly optimized for efficiency in normal flight. Settings like degraded climb thrust, save fuel, reduce engine wear, it's all very smart. But crucially, built right alongside that efficiency are very clear, very specific procedures for accessing maximum performance when safety demands it. The system isn't just about being efficient, it's fundamentally about being safe. The key here is that precise instruction. Advance the thrust levers past the derate limit only when you need more thrust on both engines for acceleration or climb, like clearing terrain, and this is non-negotiable only when no engine failure has occurred. That manual intervention by the pilot, pushing those levers, is the designed direct way to get that life-saving climb rate.
Yeah, it really highlights a constant interplay between automation, efficiency, and the pilot's ultimate responsibility and judgment. It's not just about following a checklist, it's about understanding the why behind each step, especially when things don't go as planned. It's about knowing when to let the system work and exactly when and how to take decisive manual control based on a rapid assessment of the situation. And maybe for you listening, it prompts a thought. Think about other complex systems in our lives, maybe in technology, maybe in emergency response, even everyday things. How many have these kinds of built-in overrides or emergency protocols designed for when the unexpected happens? And perhaps more importantly, how well do we actually understand the specific conditions under which they're meant to be used? It's a fascinating question that stretches way beyond the flight deck.